Have you ever wondered why some people are incredible endurance athletes while others excel in explosive power sports? The answer lies in the different types of muscle fibers that make up our skeletal muscles. Today, we're going to take a deep dive into the various muscle fibers, including how they function, generate energy, and support different types of physical activities. By the end, you'll have a comprehensive understanding of the different muscle fiber types and how they contribute to every movement we make. Let's jump in. Skeletal muscle fibers are categorized into two main types: slow twitch, type 1 fibers, also known as slow oxidative fibers, and fast twitch fibers. Fast twitch fibers are further subdivided into fast oxidative, type 2A, and fast glycolytic, type 2X, fibers. These classifications are based on two key factors: the speed of contraction and the metabolic pathways used to produce ATP, the energy molecule essential for muscle contractions. So as shown, most muscles in the body have a mix of slow twitch and fast twitch fibers, but the dominant fiber type determines the muscle's primary function and its capacity for different activities. Let's take a closer look at a muscle cell, also known as a myocyte. Each myocyte contains a unique cytoplasm called sarcoplasm, which is filled with myofibrils, long cylindrical filaments responsible for muscle contraction. These myofibrils are organized into shorter segments known as sarcomeres, which are the basic functional units of a muscle. Each sarcomere contains two main types of contractile proteins: thick filaments made up of myosin proteins, thin filaments composed of actin, along with regulatory proteins tropomyosin and troponin. The myosin filaments have club-like extensions called myosin heads. These heads play a critical role in the contraction process by binding to specific active sites on the G-actin proteins that make up the thin filament. Before a myosin head can bind to actin, it needs to gain energy. The myosin head acts as an ATPase enzyme, which means it can split ATP into ADP and a phosphate ion, releasing energy in the process. This energy cocks the myosin head into a high energy position, like pulling back a spring. Once the myosin head is in position, it binds to the active site on the actin filament, forming a cross bridge. This binding triggers the release of the stored energy, and the myosin head pulls the actin filament towards the center of the sarcomere in a movement called the power stroke. The combined power strokes of all the myosin heads sliding the thin filament along the thick filament cause the muscle fiber to contract. This process continues as long as calcium ions and ATP are available, allowing repeated cycles of cross-bridge formation and power strokes. The speed at which a muscle fiber contracts depends on the specific type of myosin ATPase enzyme present in the myosin head. There are two forms of this enzyme. Slow twitch fibers contain ATPase that hydrolyzes ATP more slowly, resulting in slower contractions. Fast twitch fibers have ATPase that hydrolyzes ATP quickly, allowing for rapid contractions. Skeletal muscle fibers rely heavily on glucose as the main source of energy. Glucose can be stored in the muscle fibers as glycogen through a process called glycogenesis. When energy is needed, glycogen is broken down into glucose via glycogenolysis. There are two main pathways for generating ATP: aerobic respiration. This is the most efficient pathway for ATP production and occurs when oxygen and mitochondria are available. Here's how it works. Glucose undergoes glycolysis in the sarcoplasm, producing two molecules of pyruvate and 2 ATP. If oxygen is present, pyruvate is converted into acetyl-CoA, which enters the citric acid cycle within the mitochondria. This process produces NADH, which drives oxidative phosphorylation in the mitochondria, generating up to 38 ATP per glucose molecule. Anaerobic glycolysis. This occurs in the absence of oxygen and is much quicker but less efficient, producing only 2 ATP per glucose. In this process, pyruvate is converted into lactic acid, which enters the bloodstream and travels to the liver for conversion back into glucose through a process called the Cori cycle. Let's delve deeper into each type of muscle fiber and understand their unique characteristics. 1. Slow oxidative fibers, type 1. The endurance specialists. Contraction speed, slow due to ATPase activity that hydrolyzes ATP at a slower rate, primary metabolism. Aerobic respiration, which provides a steady and sustained supply of ATP. Size, small in diameter, meaning they produce less force. Blood supply, rich network of blood vessels, providing a continuous supply of oxygen. Myoglobin content, high levels of myoglobin, which binds and stores oxygen, giving these fibers a red appearance. Mitochondria, numerous, supporting efficient ATP production. Glycogen stores, low, as these fibers primarily use aerobic metabolism. These fibers are ideal for endurance activities like marathon running or maintaining posture for long periods. Fast oxidative fibers, type 2A. The all-rounders, contraction speed, fast, thanks to a quicker ATPase enzyme, primary metabolism. uses both aerobic respiration and anaerobic glycolysis. Our bodies are truly remarkable, adapting to different activities by using a mix of slow oxidative, and fast glycolytic muscle fibers. Whether you're training for a marathon or a sprint, understanding these fibers can help you optimize your training and performance. If you want to test your knowledge further or explore more topics in muscle physiology, check out the King of the Curve app. It's packed with quizzes and interactive resources designed to help you master complex concepts. Don't forget to like, subscribe, and share this video for more in-depth insights into the human body. Thanks for watching.